Kepler-442b may be one of the best candidates for life we have ever found, yet we have never seen its surface at all. All we really have are a few hard numbers, and they point to a world with stronger gravity, redder light, and just enough of the right conditions to keep the life question open. But this is not a story about another Earth. It is a story about how strange a living world might be when it grows under very different rules. But before we continue, please subscribe to the channel to give your support. Let's continue. How can a planet become one of the most serious candidates for life when we have never seen its surface at all? That is the starting point with Kepler-442b. You are not dealing with a photographed world. You are not dealing with maps, clouds, oceans, or even a direct image. You are dealing with a tiny change in starlight, and everything else comes after that. The first hard fact is almost unbelievably small. Kepler-442b was detected because the Kepler telescope saw the light from its star drop by only about 0.05 to 0.06%. That drop lasted about 5.6 hours, and it repeated every 112.3 days. That is the basic signal. That is the whole reason this planet entered the conversation. So when people talk about life on Kepler-442b, they are starting from a flicker so small it would be easy to ignore if the data were not precise enough. And that immediately creates a tension. If the first evidence is that small, why did this planet become so important? Because the measurements that do hold up are exactly the kind that make scientists pay attention. Kepler-442b is listed at about 1.34 times Earth's radius. It orbits its star at about 0.409 times the Earth-Sun distance. Its orbit also appears to have low eccentricity, around 0.04, which means it is not taking some wildly stretched path around its star. Put that together and you get the kind of planet that stands out fast. It is not a giant planet. It is not a world hugging its star so closely that habitability is basically out of the question. It sits in the much more interesting category, a small temperate planet around a cooler star. But that creates the next problem. The planet is real. The measurements are real, but the picture people form in their heads is still mostly invented. Kepler-442 is about 366 parsecs away, roughly 1,190 light-years from Earth. The star is also faint, around magnitude 15.3 in visible light. So this is not a nearby system where astronomers can easily follow up and start building a detailed picture. The reason Kepler-442b became famous is not because we know what kind of surface it has. The reason it became famous is because even with very limited information, the numbers put it near the top of the list of potentially habitable Kepler planets. And that leads to an even more important warning. Even the mass number needs to be handled carefully. NASA's catalogue lists the planet at about 2.36 Earth masses. That sounds precise, but this was not the kind of direct mass measurement you get when a planet clearly pulls on its star and produces a strong radial velocity signal. The original validation work already warned that the Doppler signals for planets like this were expected to be too small for robust dynamical confirmation. So there is a very clear scientific limit here. The radius is better constrained than the composition. We have a reasonable estimate for its size. We do not have the same confidence about exactly what kind of planet it is internally. Why does that matter so much? Because once you move from this planet exists to could life exist there, composition becomes critical. A world can have a promising orbit and still turn out to be the wrong kind of planet. It could be rocky, it could be water-rich in ways that completely change the surface. It could carry a volatile envelope that makes the whole Earth-like picture misleading. So even before you get into climate, atmosphere, oceans, seasons, or biology, Kepler-442b is already forcing you to slow down. Small and temperate does not automatically mean Earth-like. So why did this planet move so quickly into the habitability discussion anyway? Because when researchers started ranking exoplanets by factors like size, incoming starlight orbit, and the chance of being rocky, Kepler-442b scored unusually well. A 2015 habitability ranking gave it a score of 0.836, slightly above Earth's 0.829 in that specific framework. That does not mean it is better than Earth. It does not mean the surface is mild, breathable, or inhabited. It means that within that model, Once the known data were combined, this planet landed very near the top of the list of worlds worth taking seriously. That is an important distinction, because a lot of bad exoplanet storytelling starts right there. A high habitability score does not mean a planet has passed some final test. It means the available numbers keep it in the fight. Kepler-442b became famous because it sits close to the right boundaries, not because it has already been confirmed as a second Earth. In fact, the opposite is true. The more carefully you look at it, the more obvious it becomes that this world is defined by uncertainty. That uncertainty is exactly why this planet is scientifically interesting. If Kepler-442b were clearly a gas dwarf, the conversation would be over. If it were clearly a scorched rock, the conversation would be over. If it were close enough and bright enough for easy atmospheric analysis, many of these arguments would already be settled. Instead, it sits in the hardest zone, the zone where the known measurements are strong enough to support real habitability questions, but weak enough that multiple very different versions of the planet are still possible. That is why this discovery matters beyond just one planet. Kepler-442b forces a more disciplined way of thinking about habitability. It shows how little data you can have and still end up with a serious scientific candidate. At the same time, it shows how dangerous it is to jump from potentially habitable to basically Earth. Those are not the same thing, not even close. A planet can be the right size in a promising orbit and still fail for reasons hidden in its atmosphere, interior, chemistry, or stellar history. So the opening truth about Kepler-442b is not that it is alive, or Earth-like, or even definitely rocky. The opening truth is that a very small signal led to a very big question. A repeating dip in starlight told us that a planet exists. A few catalogue values told us that the planet might sit in a useful temperature range. A habitability ranking pushed it into the spotlight. But the actual world behind those numbers is still largely unknown, and that is where the tension rises instead of falls. Because once you accept that the surface is not directly known, the next question becomes much more important than most people expect. The star now takes over the story. The type of star, the colour of its light, the amount of energy it gives off, and the way it behaves over billions of years will shape almost everything that life on Kepler-442b would have to deal with. So the real starting point is not just the planet. It is the star, because the star changes the rules before life even gets a chance. How much can the star change before the whole idea of life starts changing with it? With Kepler-442b, that is not a side question. That is the main question, because the host star is not the Sun, and once you understand that, the whole picture shifts. Kepler. 442 is a K-dwarf. It is cooler than the Sun, smaller than the Sun, less massive than the Sun, and much less luminous. Its effective temperature is around 4,400 Kelvin. Its radius is about 60% of the Sun's. Its mass is about 61% of the Sun's. And depending on which stellar solution you use, it puts out only around 12 to 13% of the Sun's total luminosity. That means life on Kepler-442b, if it exists, would not be growing under the same energy conditions that shaped Earth. It would be developing under a dimmer star, a redder star, and a star that burns its fuel more slowly. That point matters immediately, because people hear habitable zone and often think it means roughly Earth conditions moved closer in or farther out. That is not how this works. A habitable zone is not a copy-paste setting. It only tells you the distance range where liquid water might be possible under the right atmospheric conditions. It does not mean the sunlight looks the same, the radiation history is the same, or the biological opportunities are the same. On Kepler-442b, even if the planet sits in a useful temperature range, the energy reaching the surface would come in a different spectral mix from the start. So life there would not just be Earth life moved to a new address. It would be life trying to solve the problem of survival under a different kind of star. And that is exactly why K-dwarfs are so important in astrobiology. They sit in a middle category that many researchers take very seriously. Sun-like G-stars can work, obviously, because Earth proves that. But they do not last forever on the same terms, and they have their own limits. Red dwarfs, the smaller M-stars, are extremely common, and they live a very long time. But they can also be violent, especially early on. Their habitable zones sit very close in, and that exposes planets to more of the star's activity. K-dwarfs sit between those two cases. They are longer lived than stars like the Sun, but usually less extreme than many red dwarfs. That is why NASA and others have sometimes described K-dwarfs as a kind of Goldilocks category. Not because they guarantee habitability, but because they may offer a more balanced setup than either side. So if life exists on Kepler-442b, it is not getting the Earth deal, but it may be getting one of the more promising alternatives nature allows. It would have a star that can stay stable over long timescales while still being less punishing than the harsher end of the red dwarf population. That does not prove anything about the planet, but it changes the kind of possibilities you have to consider. Suddenly, the idea of a long-lived biosphere is not just speculation. It becomes something the star type itself can support in principle. Then the next question gets more serious. Is the radiation environment actually better, or does the star still create major problems? This is where K-dwarfs start looking genuinely attractive, but only if you stay precise. Studies from the HAZMAT program found that a habitable zone planet around a K-star can receive far less ultraviolet and X-ray radiation than habitable zone planets around many M-dwarfs. The reductions are not small. Depending on the comparison, the incoming high-energy flux can be several times lower than for early M-dwarfs and vastly lower than for late M-dwarfs. That matters because high-energy radiation does real damage. It can erode atmospheres over time. It can alter chemistry in the upper atmosphere. It can make surface conditions harder for biology, especially if the planet lacks strong protection from air, oceans, ice, or magnetic shielding. So Kepler-442 is not automatically safe, but it is also not in the worst category people worry about most. That is an important distinction. A lot of the fear around planets orbiting cool stars comes from the most active red dwarf cases, where flares, extreme ultraviolet radiation, and strong early activity can make habitability much harder to sustain. Kepler-442 does not automatically fall into that regime. That alone makes the system more interesting. But this is where the easy version of the K-dwarf story breaks down. The advantage is real, but it is not absolute. Later HAZMAT work complicated the picture. Some of that research showed that K-star ultraviolet output can stay relatively steady for a long time, extending well beyond the earliest part of stellar history before dropping significantly at older ages. Other work argued that the ultraviolet advantage of K-dwarfs over M-dwarfs is weaker than some of the earlier optimism suggested. Even if K-dwarfs may still keep an X-ray advantage in some cases, that means you cannot just look at the stellar class and declare the problem solved. Kepler-442b may sit in a more promising system than many red dwarf planets, but that does not mean the local environment is quiet. And that is exactly where the tension gets stronger. Because habitability is not only about whether the star is less dangerous than another star, it is about whether the planet can stay stable under that star's full history. Life does not only have to survive today's conditions, it has to survive the star's early behaviour, its ultraviolet output over time, its flare pattern, its changing radiation environment, and the way all of that interacts with air, water, chemistry, and atmospheric loss. A planet can sit in the right orbital zone and still lose the conditions needed for life if the star's history pushes it too hard early on. So from the first photon onward, life on Kepler-442b would be operating under different rules than life on Earth. The light would be redder. The balance between visible light and near-infrared light would be different. The ultraviolet environment would have its own timeline. The flare history would not match the Sun's. The long-term evolution of the star would also be different, because K-dwarfs can remain useful for extremely long periods. All of that matters, because life does not respond only to total energy. It responds to the kind of energy, the stability of that energy, and the damage that comes along with it. That changes the whole framing of the planet. The real question is not whether Kepler-442b is Earth 2.0. That description is too simple to be useful. The real question is what kind of biosphere a world like this would try to build under a K-dwarf over billions of years. Would the different light favour different pigments? Would the radiation history slow the development of surface life, but still allow protected environments to thrive? Would the longer stellar lifetime give evolution more time to experiment, adapt, and spread? Those are the serious questions because once the star changes, biology no longer gets to follow Earth's script. And this is where the planet stops being just another potentially habitable headline and starts becoming a deeper test of habitability itself. If the star is dimmer, redder, longer lived, and only partly less hostile than an M-dwarf, then life on Kepler-442b would not just need to exist. It would need to survive a very specific set of stellar rules and then make use of them. That is why the star changes everything before life even gets a chance. It sets the energy budget. It shapes the spectrum. It controls the radiation environment. It influences atmospheric survival. It defines how long the planet gets to remain in the game. And once you accept that, the next question becomes even more physical, because before life can use light, chemistry, or time, it has to deal with something more immediate. It has to deal with the weight of the planet itself. What would life notice first on Kepler-442b? Before light, before weather, before seasons. It would notice weight. If this planet is rocky, gravity would be one of the first things shaping everything that happens on the surface, and the change would be strong enough to matter at every scale. Using the catalogue values, about 2.36 times Earth's mass and 1.34 times Earth's radius, the surface gravity comes out to about 1.31 g, assuming the planet is in fact a rocky world. That means gravity would be about 30% stronger than on Earth. That is not a tiny adjustment. That is a basic environmental rule. Every movement would start from a heavier baseline. Walking would cost more. Climbing would cost more. Standing tall would cost more. Structures would need more support. Falling water would behave differently. The atmosphere would settle differently through altitude. Even the shape of rain waves and airborne particles would be affected by the simple fact that the planet pulls harder. That matters because people often talk about habitability as if the main question is temperature. Temperature matters, but gravity is much more basic than that. Gravity sets the mechanical cost of being alive. On Earth, a huge amount of biology is shaped by the fact that organisms must support themselves, move their fluids, transport nutrients, and resist collapse under 1g. On Kepler-442b, if the gravity really is around 1.31 g, all of those costs increase. Not enough to make life impossible, but enough to push biology in different directions from the start. Then the next question makes the planet more interesting instead of less. If gravity makes life harder, does it also help in some other way? Yes, it can. Using the same mass and radius estimates, the escape velocity is about 1.33 times the Earth's. In simple terms, the planet holds on to gases more strongly. Molecules need more speed to escape into space. That changes the long-term behaviour of an atmosphere. All else being equal, a world like this can be better at retaining air. So the same gravity that makes surface life more demanding can also make the planet more protective of the atmosphere that life would depend on. That is one of the most important tensions in the whole Kepler-442b story. The planet may be physically tougher for organisms, while also being better at keeping the ingredients needed for long-term habitability. Heavier gravity can be a burden for body plans, but an advantage for atmospheric persistence. That is exactly the kind of trade-off that makes this planet scientifically compelling, because it refuses to be simple. Every time one feature looks harder than Earth, another feature looks potentially more stable than Earth. But this is where the word super-Earth can become misleading if you use it carelessly. Bigger does not automatically mean better. A heavier rocky planet can hold on to gases more effectively, but that also means it could build a denser atmosphere, stronger pressure differences, and possibly a very different climate system from Earth's. The interior may also evolve differently over billions of years. Heat loss, tectonic behaviour, volcanic outgassing, mantle dynamics, all of that may change when the planet is larger and more massive than Earth. Kepler-442b sits above a true Earth twin in size, but still below the range where size alone starts making something Neptune-like the obvious expectation. So it lands in a very awkward middle zone. Rocky is plausible. Surface habitability is plausible, but Earth-like is absolutely not guaranteed. That middle zone is exactly where the life question becomes more realistic. Instead of asking whether there could be familiar forests, animals, or landscapes, you have to ask what kind of biology actually makes sense under this kind of gravity. Under roughly 30% more surface gravity, tall, fragile structures become more expensive to build and maintain. Powered flight becomes harder because wings need to generate more lift against a stronger pull. Surface movement favors lower, sturdier, more mechanically efficient forms, unless some other factor like water or dense air offsets the problem. So the real question changes fast. Not would there be animals like ours, but would this world favor microbial mats, compact vegetation, aquatic ecosystems, low-slung multicellular life, or powerful organisms built close to the ground? That is not speculative decoration. That is just biomechanics. A stronger gravitational field changes, which shapes are cheap and which are expensive. On Earth, tall trees work because wood can support height under 1g, while fluid transport and mechanical stress stay within workable limits. On a heavier world, height becomes costlier. A body plan that looks efficient here may become a wasteful design there. The same logic applies to limbs, skeletons, musculature, circulation and movement. If life on Kepler-442b became complex, there is a good chance it would look more compact, more reinforced, and less extravagant in open air than many Earth organisms. But then the planet gives something back again. Stronger gravity may help make the biosphere more durable over long timescales. A world that holds onto its gases more effectively may be better at preserving climate stability, especially if atmospheric loss would otherwise be a major threat. If the planet can retain more of the volatile inventory needed for a long-lived atmosphere, that could help keep surface pressure, greenhouse warming, and water stability in the range life needs. So the surface may be harder, but the global system may be more persistent. Tougher local conditions, potentially more reliable planetary conditions. That is the deeper pattern with Kepler-442b. It does not just look promising or difficult, it looks both at once. More gravity means more strain on movement and structure. More gravity also means a better grip on the atmosphere. A larger planet may be less Earth-like in the details, but it may also be less fragile in ways that matter for habitability. The same property that raises the cost of life may help preserve the stage life needs. And once you see that, the planet becomes harder to simplify. It is not enough to say it is bigger than Earth. Bigger changes mechanics, climate, atmospheric retention, and probably long-term planetary evolution. It changes what kind of life is likely, what kind of air can last, and how the surface environment behaves over billions of years. Kepler-442b is not interesting because it looks like Earth at first glance. It is interesting because it might support life through a very different physical balance. That balance would affect every living thing on the planet, from the smallest surface organism to the largest possible multicellular body. If life exists there, it would not just need chemistry and water. It would need designs that work under a heavier pull. It would need ecosystems built around a more demanding surface. And if that surface is difficult, then the next question becomes even more important. Because life does not only live under gravity, it lives inside time. And on Kepler-442b, time may work very differently from Earth. How different can life become if the basic clock of the planet is different from the start? On Kepler-442b, time itself may not work in a familiar way. And that matters much more than people usually think. Because biology does not only need water, air, and energy, it also needs timing. It needs regular patterns. It needs cycles that tell living systems when to grow, when to rest, when to migrate, and when to store energy for harder periods. The first big difference is the year. Kepler-442b goes around its star once every 112.3 days. That means its entire year is only about a third of an Earth year. So if the planet has climate rhythms, biological seasons, blooms, die-offs, migrations, feeding pulses, all of that would be running on a much shorter yearly clock than it does on Earth. That is not a cosmetic detail. On Earth, ecosystems are built around timing. Plants respond to seasonal light and temperature changes. Predator and prey cycles often depend on narrow windows. Carbon storage and release also follow seasonal patterns. If Kepler-442b hosts life, that life would not just live on another planet. It would live inside a different calendar. But a short year does not automatically mean violent seasons. That is the next important correction. The planet's listed orbital eccentricity is small, around 0.04. In simple terms, the orbit does not appear to be strongly stretched. So Kepler-442b is probably not rushing very close to its star and then swinging far away again in some extreme cycle. That matters because large eccentricity can create strong seasonal energy swings just from orbital geometry alone. Mars is a familiar example of how an odd orbit can complicate climate. Kepler-442b does not immediately look like that kind of case. So if this world has major seasonal variation, the main cause is probably not the orbit by itself. The bigger causes would more likely be atmospheric properties, the tilt of the planet's axis, how quickly it rotates, how the oceans move heat, and how cloud systems form and persist. That changes the whole way you should think about the climate. The short year sets the clock, yes, but it may not produce big familiar seasons unless other planetary factors amplify it. And that leads directly to one of the biggest unknowns in the whole system. We know the length of the year. We do not know the length of the day. That missing number is a huge problem, because rotation period is one of the most important climate variables on any planet. If Kepler-442b rotates quickly, the atmosphere could organize itself in one way. If it rotates slowly, the circulation could be very different. If it is close to synchronous rotation, where one side tends to face the star more persistently, then the climate could shift again into another regime entirely. Wind patterns, cloud bands, storm behavior, ocean heat transport. The contrast between day and night. All of that depends heavily on the spin state. This is where a lot of people jump too fast to the most extreme image and get it wrong. Kepler-442b is not automatically a tidally locked world with one permanent day side and one permanent night side. That is possible, but it is not the only live option, and it is not even the one you have to assume first. A 2024 study looking at photosynthesis under K-dwarf light used a 12-hour day-night cycle, in part because Earth-like planets near the centres of habitable zones, around K-dwarfs above roughly half the Sun's mass, are often treated as being outside the simplest tidal lock range. Kepler-442's star is around 0.61 solar masses, so there is no scientific reason to force the whole planet into the classic eyeball world picture as the default. That matters because the climate consequences are huge. If the planet is not tightly locked, then the surface may experience a real moving day-night cycle, and that changes heat distribution, atmospheric circulation, and the way ecosystems would organize themselves. Dawn and dusk would matter. Surface temperatures could be moderated differently. Photosynthetic life, if it exists, would not have to evolve only around permanent day or permanent darkness. On the other hand, if the planet rotates slowly, the day-night cycle might still be very long compared with Earth's, and that would create its own problems. Long hot days, long cool nights, different wind systems, different storage strategies, different ecological pacing. So even without full tidal locking, the unknown day length keeps several very different worlds alive at once. And that is what makes the time problem so important. Life there might not organize itself around anything humans would consider normal. You could have a short year, but only weak orbital seasons. You could have a day length that is fast, slow, or in some intermediate state. You could have redder light from the K-dwarf changing how useful different parts of the daylight spectrum are at different times of day. So the biological meaning of morning, noon, evening, and season could all drift away from the Earth model. Think about what that does to living systems. Circadian biology on Earth is built around a 24-hour cycle because the planet rotates once in that time. Seasonal biology is built around a 365-day orbit. On Kepler-442b, both layers may be different. If the year is only 112 days, then the annual pacing of ecosystems compresses. If the day length is also different, then the daily pacing changes too. That would affect how organisms store energy, how long they remain active, when they bloom, when they hunt, when they rest, and how entire food webs line up with each other. And those changes do not have to look dramatic from a distance to be profound. This is not just about bigger storms or stranger skies. It is about the internal logic of the biosphere. A world with short years might favour faster ecological turnover in some environments. A world with muted orbital seasonality might reduce the pressure for strong annual migration cycles. A world with long days or slow rotation might reward organisms that can tolerate long exposures and long recoveries instead of Earth-like daily rhythms. A world with redder light may even shift which times of day are most biologically productive. So when you ask what life on Kepler-442b would look like, time is not some background detail. Time is part of the environment. The clocks of the planet may not match the clocks life evolved under on Earth, and that means the structure of living systems could diverge in ways that are deep, not superficial. The cycles of growth, feeding, storage and recovery may all be tuned to a planet where the year is short, the seasons may be weaker than expected, and the rotation is still unknown. That is why time would stop behaving like Earth time. On Kepler-442b, the orbital clock is already different. The daily clock is still unresolved. The climate rhythm may depend more on air and spin than on orbit alone. And once those clocks change, life does not just continue on a different schedule. It starts becoming a different kind of biosphere. And that brings the next problem into focus. Because once life has to live under a different star, stronger gravity, and an unfamiliar clock, the next thing that matters is the light itself. Not just how much arrives, but what kind of light it is, and what that does to the whole energy economy of the planet. Why would the colour of the star matter so much if the planet is still in a habitable zone? Because on Kepler-442b, daylight would not just look different, it would change how the whole planet works. The star is cooler than the sun, around 4,400 Kelvin, instead of about 5,778. And that means its light is shifted toward longer wavelengths. In simple terms, the planet would receive redder light, with a different balance between visible light and near-infrared light. So even if the total energy is in a useful range, the type of energy is not the same as Earth gets. That matters immediately for climate. Different wavelengths interact differently with air, water, ice, and living tissue. A redder star does not just make the sky feel slightly warmer in colour. It changes heating patterns, it changes atmospheric chemistry, and it changes which parts of the spectrum biology can use most effectively. So the surface of Kepler-442b would not just be Earth with dimmer sunlight. The energy system of the whole planet would be built around a different kind of daylight from the start. One of the biggest climate effects shows up in something very simple: ice and snow. On Earth, bright ice reflects a lot of incoming sunlight, and that helps drive the familiar feedback loop, where more ice can mean more reflection and therefore more cooling. But around a redder star, that logic weakens. Ice and snow reflect less efficiently at longer wavelengths. Once you move into that redder part of the spectrum, the contrast between bright ice and darker open water becomes smaller. That means frozen surfaces do not bounce energy back as effectively as they do under sunlight like ours. This is a major change, because it means a planet around a K-dwarf can resist full snowball collapse differently from Earth. On our planet, once ice spreads far enough, the reflection effect can become a serious climate amplifier. On Kepler-442b, that amplifier would be weaker. Ice would still matter, cold would still matter, but the planet would not behave exactly like Earth under cooling pressure. A colder K-dwarf world may be better at holding onto partially open oceans or temperate regions than an Earth-based intuition would suggest. So right away, the redder daylight is affecting not just what life sees, but whether liquid water can stay available in the first place. Then the biological side gets even more interesting. On Earth, photosynthesis evolved under one star, the Sun, and over time life built very successful systems around the light that star provides. On Kepler-442b, the incoming photon supply would be different. Not absent, not useless, but shifted. That means any light harvesting biology would be working on a different battlefield. The pigments that do best, the wavelengths most worth capturing, the structure of photosynthetic tissues, even where living things choose to grow, all of that could shift in response. If the atmosphere also filters the bluer end of the spectrum more strongly, then the pressure to use longer wavelengths efficiently could become even stronger. So instead of asking whether alien plants would just be green or not green, the more serious question is much deeper. What kind of biological design becomes most effective under this kind of star? Would phototrophs stay near shallow water where light is strongest? Would low-profile mats dominate, because they can harvest diffuse light efficiently. Would more complex surface organisms evolve broader pigment systems tuned to a redder spectrum? Those are the kinds of changes the light environment can push. And this is where the science becomes much more grounded than people expect. We do not have to treat K-dwarf photosynthesis as pure speculation. There is lab evidence that this kind of light can support meaningful photosynthetic activity. A 2024 study exposed garden cress and the cyanobacterium crucoccidiopsis to simulated K-dwarf illumination meant to represent a habitable zone planet with an Earth-like atmosphere. The result was not that photosynthesis collapsed under alien light. The garden cress showed photosynthetic efficiency comparable to what it showed under solar conditions. The cyanobacterium, in some measurements, actually performed significantly better under the K-dwarf light than under sunlight. That does not prove Kepler-442b has forests, or even surface life at all, but it does remove one of the lazy assumptions people make. A redder star does not automatically mean light-driven life is weak, marginal, or impossible. It means the biological design space changes. It means the most successful organisms might not look or function like the dominant photosynthetic life on Earth. But the basic idea of oxygenic photosynthesis, like metabolism, remains scientifically plausible. That is a very important shift, because once that becomes clear, the whole habitability discussion gets more serious. Kepler-442b is not automatically too dim. It is not automatically too red. It is not automatically too far from Earth's light environment for productive phototrophy to work. The better question is what architecture life would develop under those conditions. Would the biosphere be dominated by microbial films, shallow marine phototroughs, cold water specialists, low-light surface communities, or compact land organisms if land exists at all? The answer depends on far more than just light, but light no longer kills the idea. And this also changes how you think about productivity. On Earth, when people imagine alien life under a cooler star, they often assume the planet must be biologically weaker by default, less active, less productive, less able to support large-scale biospheres. But that is not a safe assumption here. If the atmosphere is workable and liquid water is stable, a K-dwarf world can still provide enough useful energy for a real biosphere to take hold. The challenge is not simply whether life gets photons. The challenge is how life organizes itself around a different spectrum and around climate systems that may favor oceans, cold margins, patchy temperate zones, or sheltered environments. That makes Kepler-442b much more interesting than the simple version of the story. The simple version says the star is dimmer, so the planet must be worse for life. The more accurate version says the star is dimmer and redder, so the rules are different. Ice reflects differently. Atmospheres process incoming energy differently. Biology gets a different set of wavelengths to work with. And once you put those pieces together, the planet stops looking like a weak copy of Earth and starts looking like a world that could support life in a different but still serious way. So the biosphere there, if one exists, is not starved by default. That is the key point. The real question is not whether light-driven life can work at all. The real question is what kind of living system emerges when the spectrum shifts, the climate responds differently to ice, and the most efficient biology may be built for redder light, lower contrast, and different environmental niches than the ones that dominated Earth. And that leads straight into the next problem, because once you accept that the light may be usable, the planet becomes harder to dismiss and harder to simplify. Then the focus moves to the part that decides almost everything else, the climate itself. Because Kepler-442b can only become a real living world if the atmosphere, clouds, greenhouse balance, and incoming energy all work together in the right way. When does a promising planet stop sounding exciting and start becoming difficult? It happens when you get to climate. This is the point where Kepler-442b stops being a nice habitability headline and turns into a real scientific problem. Because being in a good-looking orbit is not enough. The planet has to actually stay warm in the right way, keep liquid water stable in the right places, and avoid becoming either a frozen world or a planet buried under the wrong kind of atmosphere. The first trap is equilibrium temperature. You will often see numbers for Kepler-442b that put its equilibrium temperature somewhere around 241 to 260 Kelvin, depending on which archive fit you use. That is below the freezing point of water. And if you stop there, the planet starts looking too cold. But that is exactly why equilibrium temperature by itself is a bad shortcut. It is not the surface temperature. It is just a simplified estimate of how warm the planet would be if you treated it like a basic energy balance object with no real atmosphere doing any serious work. Earth is the perfect reminder of why that shortcut fails. If you calculate Earth's equilibrium temperature, you also get a number below freezing. But Earth's real surface is much warmer because greenhouse gases, clouds, oceans, and atmospheric circulation all change the result. The air traps heat. Water moves heat around. Clouds reflect some energy and hold in some energy. The whole climate system matters more than the simple estimate. So if Kepler-442b has liquid oceans, stable surface water, or broad temperate regions, it would not be because the equilibrium temperature solved the problem on its own. It would be because the atmosphere and circulation solved it. Then the uncertainty gets worse, because even the incoming energy is not one fixed number. Different archive solutions put the stellar flux in different places. One fit gives it about 66% of the energy Earth receives from the Sun. Another puts it closer to 91%. Older catalogue solutions even reached roughly 108%. That is not a tiny bookkeeping difference. That changes the entire climate picture. A planet getting around 2/3 of Earth's energy is a very different case from a planet getting almost the same amount Earth gets, and both are different again from a planet getting slightly more. That means Kepler-442b is still sitting in a wide zone of climate possibilities. At the lower end, you can start picturing a cool world that needs a strong greenhouse effect just to keep large bodies of water liquid. In the middle, you can picture something more temperate, where the atmosphere still matters a lot, but the incoming energy is already close enough to support a broad, stable climate under the right conditions. At the upper end, you could be dealing with a warmer world, where the danger is not freezing first, but whether the atmosphere and hydrology push the planet into a more humid, thicker air, less Earth-like state. This is exactly why habitability papers keep pulling Kepler-442b back into the conversation. In one influential framework, Barnes and colleagues argued that planets getting roughly 60 to 90% of Earth's incoming radiation on near-circular orbits are among the strongest candidates for habitability. Their table placed Kepler-442b at about 81% of Earth's flux, with a very high habitability score. That does not settle the climate at all. It does something more important. It shows why the climate argument is worth having in the first place. The planet is close enough to the right range that its atmosphere and surface conditions become the deciding factor, instead of the orbit killing the idea immediately. And that is where the whole world starts depending on heavy atmospheric lifting. If the air is too thin, the surface likely freezes, or spends most of its time on the edge of freezing. If the greenhouse effect is too weak, equilibrium wins too much of the battle, and the planet stays cold. But if the atmosphere is too thick, too volatile rich, or built from the wrong inventory of gases, then the problem changes in the opposite direction. Now, the planet may stop looking like a rocky surface world at all. It may turn into something deeper, denser, steamier, or more like a mini Neptune in behaviour than an Earth-like habitable planet. That is why the phrase potentially habitable is so dangerous with Kepler-442b. It sounds like the planet is almost understood, when really the hardest part is still unresolved. This world may only work if the atmosphere is doing exactly the right amount of work. Not too little, not too much. Enough greenhouse warming to lift the surface into a clement range. Enough pressure to stabilise liquid water. Enough circulation to move heat. Enough cloud behaviour to avoid runaway extremes. But not so much volatile retention that the whole familiar rocky surface scenario breaks down. And if that balance is there, then Kepler-442b becomes one of the most serious K-dwarf habitability cases anyone could ask for. It would mean that a planet heavier than Earth, orbiting a dimmer and redder star, with a shorter year and different light environment, still found a stable climatic path to surface habitability. That would be a huge result, even in theory, because it would show that Earth's recipe is not the only way to build a living world. It would show that different gravity, different stellar colour, and different orbital timing can still converge on something biologically useful. But the most difficult part is that the opposite cases are still alive too. Kepler-442b could be a cold marginal planet that only flirts with habitability in limited regions or limited epochs. It could be a stable ocean world with a real long-term climate system. Or it could be a volatile, rich false alarm where the radius and orbit looked promising, but the actual planet is not the kind of place surface life could use in the way people first imagined. Current data do not decisively eliminate any of those versions. That is the real tension in this planet. Not what does it look like, but how many very different planets can hide behind the same transit numbers. Because the transit gives you size and timing. It does not give you clouds, pressure, ocean depth, greenhouse inventory, atmospheric chemistry, or circulation strength. A cold, rocky world, a temperate ocean planet, and a deeper atmosphere, volatile, rich world can all fit under the same broad observational umbrella if the missing atmospheric details are different enough. And once you see that, the climate stops being a detail and becomes the core mystery. The orbit got the planet onto the list. The size kept it there. The star made it interesting. But climate is what decides whether Kepler-442b is a real living world candidate or just a very good imitation from a distance. A small shift in greenhouse gases, cloud cover, pressure, or circulation can completely change the verdict. That is why this planet is not easy. It sits close enough to habitability to matter, but with enough uncertainty left that radically different outcomes are still possible. So the climate question is not a side note. It is the place where the whole case either survives or breaks. If the atmosphere is right, Kepler-442b may be one of the most compelling temperate super-Earths around a K-dwarf. If it is wrong, the famous habitability story collapses. And right now, both outcomes are still scientifically live. That is why this world is so hard to classify. The same measurements can describe a planet that is barely holding on, a planet that is broadly temperate, or a planet that never really had the right surface conditions at all. And when one set of data can still hide that much climate uncertainty, the next question becomes unavoidable. What is actually covering the surface? If there is a surface you could stand on in the first place? What if the biggest mistake is assuming there is land at all? That is where the Kepler-442b story gets much harder, because once you move past orbit and climate, you hit a blunt limit. We still do not know what kind of surface this planet actually has. We know its radius is about 1.34 times Earth's, and that is encouraging because it places the planet below the rough statistical transition near 1.6 Earth radii, where many worlds stop looking mostly rocky and start looking more likely to hold thick volatile envelopes. That is why Kepler-442b keeps surviving these habitability discussions. Its size leaves room for a solid world. But leaves room is not the same thing as confirmed. That transition is statistical, not absolute. A planet below it can still be water-rich, volatile-rich, or more complicated than the word rocky makes it sound. Radius alone cannot tell you if the surface is mostly dry land, deep global ocean, rock under a massive water layer, or rock hidden under a thick atmosphere that changes everything above it. So even at this stage, one of the most important facts is still missing. We do not know whether Kepler-442b gives life coastlines, open oceans, buried seafloors, frozen margins, or something in between. And that matters because a deep ocean changes almost everything. If the planet is strongly water-rich, then the whole Earth-like surface picture starts to fall apart. Nutrient cycling changes, weathering changes, shorelines may be limited or absent. River systems may not exist in anything like the way we know them. Shallow coastal environments, which are often treated as biologically important on Earth, may be much less common or may look very different. Even carbon regulation can change. Because you cannot just assume an Earth-style silicate weathering cycle works the same way if continents are rare, submerged, or missing. That is a serious change in the logic of habitability. A habitable ocean planet can still be habitable, but it may not build complexity the same way Earth did, or on the same schedule. If most of the surface is deep water, then the exchange between rock, atmosphere, and ocean can become more restricted, or at least very different. If nutrients are harder to recycle into the upper ocean, productivity can become more patchy. If there are fewer continental shelves, fewer complex coastlines, and fewer stable, shallow water zones, that changes where life can concentrate and how ecosystems scale up. So even if Kepler-442b is rich in water, that does not automatically mean it is an easy cradle for Earth-like complexity. It may still host life, possibly a lot of it, but the planetary pathway could be very different. Then the redder star changes the frozen parts of the story too. This is one of those quiet results that completely changes the picture once you notice it. Around a K-dwarf like Kepler-442, ice reflects less effectively than it does under sunlight like ours. That weakens the classic feedback where more ice means more reflection, which means more cooling, which means even more ice. On Earth, that loop can become powerful. On Kepler-442b, it may be weaker. So if the planet is on the cool side of temperate conditions, it might still hold on to partial oceans or mixed climate zones more effectively than an Earth-based guess would suggest. That means a world does not need to look like a blue marble to stay biologically interesting. If there are fewer continental shelves, fewer complex coastlines, and fewer stable, shallow water zones, that changes where life can concentrate and how ecosystems scale up. So even if Kepler-442b is rich in water, that does not automatically mean it is an easy cradle for Earth-like complexity. It may still host life, possibly a lot of it, but the planetary pathway could be very different. Then the redder star changes the frozen parts of the story too. This is one of those quiet results that completely changes the picture once you notice it. Around a K-dwarf like Kepler-442, ice reflects less effectively than it does under sunlight like ours. That weakens the classic feedback where more ice means more reflection, which means more cooling, which means even more ice. On Earth, that loop can become powerful. On Kepler-442b, it may be weaker. So if the planet is on the cool side of temperate conditions, it might still hold on to partial oceans or mixed climate zones more effectively than an Earth-based guess would suggest. That means a world does not need to look like a blue marble to stay biologically interesting. So the question changes again. Not could life exist, but where would life actually concentrate? If the surface is mostly ocean, then marine biology becomes the main story. If the planet is partly glaciated, then life may cluster where light, liquid water, and nutrient mixing overlap. If there are continents, maybe only certain bands are temperate enough and wet enough to matter. If there is deep ocean over much of the world, maybe the most stable ecosystems are not on land at all, but in the upper ocean, along chemically active seafloors, or in long-lived transition zones where temperature and chemistry remain usable. This is why the land question is much more dangerous than it sounds. People hear rocky planet, and they quietly fill in the rest. They assume there must be dry ground, weathering cycles like Earth's, and enough geographical variety to support familiar ecological layering. But rocky only tells you so much. A rocky world can still be ocean-dominated, it can still be ice-heavy, it can still bury most of its surface underwater, while keeping only small amounts of exposed land, if any. And once that happens, the likely biosphere changes shape completely. It might still be vast, it might still be productive, it might even alter the atmosphere over time, but it may not resemble the land-centered biosphere humans instinctively imagine when they think about life. The dominant life on Kepler-442b, if it exists, may live in the ocean's sunlit upper layers, not on continents. It may thrive in microbial communities spread over enormous wet surfaces rather than in forests. It may build planetary-scale productivity with almost no need for anything that looks familiar from Earth's land life. That is not a downgrade. It is just a different solution, and a partly frozen version of that world is still fully in play. That matters because people often talk about habitability as if a planet must be globally mild or it somehow fails. That is not true. A planet can be cold overall and still alive. A planet can carry large frozen regions and still support strong biological activity in the places that remain open, wet, lit, and chemically useful. A planet can have patchy habitability instead of global comfort and still count as biologically important. Kepler-442b does not need to be easy to matter. It just needs to keep enough of the right environment stable for long enough. So the most dangerous assumption is still the simplest one, that land is guaranteed and that habitability automatically means landscapes we recognize. It does not. Kepler-442b could have continents, but it could just as easily be an ocean-first world, an ice-edged world, or a mixed world where the best habitats are concentrated into narrow corridors. And if that is true, then the most likely biosphere there may be huge, ancient, and highly active, without ever looking remotely like the human default picture of a living planet. That is why the surface question does not reduce uncertainty, it multiplies it. The same planet can be promising as a rocky world, promising as an ocean world, and promising as a partly glaciated world. But each version leads to a very different kind of biology, and all of those versions are still consistent enough with what we know that none of them can be dismissed casually. So by this point, the real issue is no longer just orbit, or starlight, or gravity, or even climate by itself. It becomes the thing that decides whether any of these surface versions matter at all. Because a rocky ocean world, a cold mixed world, and a continent-bearing world can all still fail for the same reason if the air above them is wrong. How can one missing thing decide almost everything about a planet? On Kepler-442b, that missing thing is the atmosphere. We do not know the air, and that is not a small gap in the story, that is the main gap. No transit catalogue value tells us the surface pressure, the cloud cover, the greenhouse gases, the oxygen level, or even how much of the planet is ocean versus land. So every version of life on Kepler-442b depends on the one part we do not actually have in hand. On this world, the atmosphere is not just one detail among many. It is the thing that decides whether the surface matters at all. That point is easy to underestimate. Because people hear size, orbit, and habitable zone, and they think they already know the basic answer. But those numbers do not tell you what it would feel like to stand there, if standing there is even possible. They do not tell you whether the surface is under thin, cold air, under crushing, dense air, under cloud decks that trap heat, or under a volatile envelope so deep that the whole Earth-like surface idea breaks apart. So once you get serious about habitability, the conversation stops being about the orbit and starts being about the atmosphere. And this is where the planet can still be saved. Or lost. A thicker atmosphere could make a huge difference. If Kepler-442b has enough air and the right greenhouse gases, that atmosphere could move heat around the globe, reduce extreme cooling at high latitudes or on the night side, and raise surface temperatures far above the simple equilibrium estimate. That is why exoplanet climate studies keep coming back to atmospheric composition and pressure as first-order controls. The orbit puts the planet in the conversation, but the air decides whether liquid water can actually stay stable. This is especially important on a planet like this, where the incoming energy may be a bit lower than Earth's, and where the equilibrium temperature by itself points below freezing. Without enough atmospheric help, the surface may spend too much of its time cold, or only allow narrow, habitable regions. With the right atmosphere, that same planet could support temperate oceans, active weather, and long-term surface water. So the dividing line between frozen and clement may not be drawn by distance from the star alone. It may be drawn by the air, but then the same feature becomes dangerous in the other direction. Too much atmosphere can create the wrong kind of world entirely. If Kepler-442b held onto a very thick, volatile envelope, the result might not be a helpful climate blanket over a rocky surface. It might be a planet where the familiar surface scenario never really exists in a useful sense. The air could become too deep, too pressurized, too rich in the wrong gases, too disconnected from anything like Earth conditions. This is where the warning about size comes back. A small super-Earth does not automatically mean a larger version of Earth. It can also mean a world where the atmosphere dominates so completely that the ground, if reachable, does not play the role people imagine. That is the real tension. A substantial atmosphere could be exactly what makes Kepler-442b habitable. A substantial atmosphere could also be exactly what makes it the wrong kind of planet. The same retention that protects the climate can also erase the version of the planet people most want to find. So again, Kepler-442b refuses to be simple. The air could save the surface, or it could bury it under the wrong conditions. Then there is another assumption that has to be stripped away. Breathable oxygen is not the default. A habitable planet does not need to start with oxygen-rich air, and life does not need to begin with anything humans could breathe. Earth itself did not have that kind of atmosphere for most of its history. Oxygen only became a major atmospheric feature after biology had already existed for a very long time, and even then it had to interact with geology, oceans, sunlight and the rest of the planet's chemistry in very specific ways. So if you are trying to stay scientifically disciplined with Kepler-442b, you do not begin by assuming blue skies and air you can breathe. You begin with chemistry. That matters because once people hear possible life, they tend to skip straight to animals, forests, lungs, and familiar ecosystems. But a living planet can be habitable without being breathable. It can host microbes, oceans, chemical cycles, and even large-scale biology without offering anything close to human comfort. So when thinking about life on Kepler-442b, the smart move is to assume the atmosphere would first need to be stable and chemically supportive for life in general, not comfortable for us in particular. Oxygen, if present, would have to be earned by the planet's history, not assumed from the start. And even oxygen, if it existed, would not solve everything. It has to be read in context. On exoplanets, oxygen can be misleading if you do not know the rest of the environment. The same goes for clouds, methane, carbon dioxide, and water vapor. One gas by itself does not tell the whole story. What matters is the full atmospheric setup, pressure, temperature structure, chemistry, stellar radiation, and surface interaction. That is why Kepler-442b remains so difficult. Even if you could detect something interesting one day, interpreting it would still depend on facts that are currently hidden. So the planet's real identity may be invisible from the outside. That is the most frustrating part. A thin, cold world with very little air, a dense ocean planet with strong greenhouse warming, a carbon dioxide-rich temperate world, and a planet with something closer to an Earth-like biosphere could all look much more similar than people expect when your data is limited to radius, period, and a shallow transit. Those numbers are enough to make the planet famous. They are not enough to settle what kind of world it really is. That is why Kepler-442b feels so difficult in astrobiology. The most important questions all point to the atmosphere, and the discovery method is especially bad at answering them. Transit data tells you something passed in front of the star. It tells you how big the object appears relative to the star. It tells you how often the orbit repeats. It does not tell you what the air feels like, how deep it is, what it is made of, how it moves heat, or whether it helps life or blocks it. So at this point, the planet is balanced on an atmospheric knife edge. Too little air, and the world may be cold, dry, or unstable at the surface. The right amount and type of air, and the planet could maintain temperate conditions over very long timescales. Too much of the wrong kind of air, and the world becomes something very different from the rocky living planet people hope for. The same missing component controls all three outcomes. That is why the atmosphere is not a detail on Kepler-442b. It is the difference between a meaningful habitable world and a false positive for habitability. It decides whether the climate works, whether surface water stays liquid, whether the star's energy becomes useful, whether the surface is protected, and whether any biosphere could become visible or remain hidden. Without the atmosphere, the rest of the story is incomplete. With the wrong atmosphere, the story collapses. With the right atmosphere, the planet becomes one of the most serious cases for a different kind of living world. And that makes the next problem even more dangerous, because even if the atmosphere is good enough, the climate does not just need to be possible. It needs to be stable in motion. It needs winds, clouds, heat transport, and weather patterns that do not destroy the same habitability the air creates. What if the atmosphere is good enough for life, but the weather keeps deciding who gets to live where? That is the next problem on Kepler-442b. A planet can have the right size, a useful orbit, and a workable atmosphere, and still end up with a climate system that makes habitability narrow, fragile, or highly uneven. On this world, weather is not some local detail. Weather may be the thing that decides whether the planet becomes broadly habitable, patchily habitable, or only habitable in a few protected zones. The hidden variable behind all of that is rotation. Rotation rate is one of the biggest climate controls on any planet, and on Kepler-442b, it is still unknown. That missing number keeps multiple very different versions of the planet alive at the same time. If the planet spins quickly, the circulation can break into one kind of pattern. If it spins slowly, the pattern changes. If it is near synchronous rotation, where one side tends to face the star for very long periods, the whole climate may reorganize again. These are not small differences. A fast rotator, a slow rotator, and a near synchronous world are not three shades of the same planet. They are three different climate systems. That matters because winds, storms, cloud cover, ocean currents, and heat transport do not form randomly. They are shaped by the way the planet turns. On Earth, the 24-hour rotation helps produce jet streams, trade winds, storm tracks, and broad circulation cells that distribute heat and moisture around the globe. Change that underlying timing, and the whole machine starts behaving differently. So when people ask what the weather would be like on Kepler-442b, the honest answer is that we still do not know, because the spin state is one of the most important missing facts in the entire system. Then the story gets stranger, because slow rotation is not automatically bad. In fact, some three-dimensional climate models have shown that slowly rotating or synchronously rotating terrestrial planets can build thick cloud decks over the region, receiving the most direct starlight. Those clouds reflect more incoming energy back into space, which can help prevent runaway surface heating. In other words, a planet that looks vulnerable because it rotates slowly can sometimes stabilize itself by growing the right clouds in the right place. That is a serious result, because it means a planet does not have to behave like Earth to protect itself. Unusual circulation can sometimes create its own climate defense. So on Kepler-442b, a slow-spinning world is not automatically a failed world. If the atmosphere is thick enough and moist enough, and if the circulation supports persistent cloud formation in the hottest region, those clouds could become part of the reason the climate stays usable. That completely changes the tone of the problem. Instead of assuming the weirdest cases are the least habitable, you have to allow for the possibility that the weird cases solve the climate problem in their own way. But the moment you change the rotation, you also change where that solution works and where it fails. Other modelling studies have shown that atmospheric dynamics on tidally locked or near tidally locked terrestrial planets can shift sharply as the rotation period changes. Different wave patterns begin to dominate. Different pressure structures take over. Different circulation modes start controlling where heat piles up, where air rises, where clouds thicken, and where surface water remains stable. In simple language, if you change the spin, you change where storms sit, where dry zones form, where wet zones persist, and where life gets the best chance to hold on. That is why weather on Kepler-442b is not just an extra layer on top of habitability. It is part of the habitability decision itself. A planet can have water and air in theory, but if the circulation keeps one hemisphere too cold, one region too dry, or one latitude band too unstable, then life may only get a narrow foothold. On the other hand, if the circulation is effective at moving heat, spreading moisture, and creating durable climate zones, the same planet can suddenly support much broader living space. The weather system is not decorating the environment, it is building the map of where biology can exist. And the most unsettling possibility is that the planet may not be fully synchronized or fully Earth-like in rotation, but stuck somewhere in between. That does not make the climate simpler. It makes it stranger. A partly synchronized world could end up with a long-lived warm hemisphere, a colder reservoir elsewhere, and stable circulation cells carrying heat and moisture between them for extremely long timescales. That would not look like Earth's shifting storm tracks moving around from week to week and season to season. It would look more like a climate structure locked into the geometry of the planet-star system. That kind of setup could reshape biology completely. If warmth, moisture, clouds, and nutrient transport keep returning to the same zones again and again over geological timescales, then ecosystems might become extremely stable in those places. You could get long-lived biological provinces, regions that stay favourable for millions of years, not because the weather is mild everywhere, but because the circulation keeps protecting the same corridors. On the other hand, that same stability could compress life into narrow belts. Instead of a planet with wide mixed habitability, you might get a world where most of the biosphere is concentrated into a few durable zones between too hot and too cold, too wet and too dry. That is the next tension. Stability is not always the same thing as generosity. A stable climate machine can create long-lived habitats, but it can also make the rest of the world hard to use. If Kepler-442b has a persistent warm region and a persistent cold region, with circulation linking them in predictable ways, then biodiversity might either be squeezed into narrow bands or organised into very durable ecological provinces that barely move over time. That would be very different from Earth, where changing seasons, shifting storm tracks and regional climate variability create a constantly moving ecological map. So the weather on Kepler-442b might not feel dramatic in the way people expect. It might not be about giant storms, constant chaos, or spectacular extremes. The more alien possibility is almost the opposite. The same cloud structures returning again and again. The same circulation corridors moving heat and moisture through the same parts of the planet. The same upwelling regions in the ocean. The same wet belts, dry belts, bright cloud zones, and biologically productive margins repeating for immense spans of time. A world where weather stops feeling like short-term variation and starts feeling like infrastructure. That would matter enormously for life. Stable cloud bands could regulate surface temperatures. Stable wind patterns could control where nutrients circulate through the air and ocean. Stable wet and dry regions could determine where photosynthetic life can spread and where it stays trapped. Stable ice margins could become some of the most productive interfaces on the planet if ocean mixing, light and chemistry line up there over and over again. So the climate system may not just permit life, it may channel life into the same geographic logic for millions or billions of years. And once you see that, the whole planet becomes more unsettling. Because Kepler-442b may not fail through obvious chaos. It may succeed through deep regularity. It may be a planet where habitability does not come from Earth-like weather variability, but from a circulation pattern that stays globally consistent for immense periods of time. That could make the biosphere very resilient in some places and very restricted in others. It could create strong, persistent habitats without ever giving the whole world equal access to them. So the big question is no longer just whether the weather is harsh or mild. The bigger question is whether the climate system creates durable living space and how much of the planet gets included. On Kepler-442b, weather may decide whether life becomes global, regional, or highly confined. It may decide whether the planet builds broad ecological complexity or a few long-lasting biological strongholds. And all of that still depends on one missing number, the rotation rate. That is why the weather could be gentle, global and stable, or completely unlike Earth's logic while still being stable in its own way. The planet might not be defined by violent chaos. It might be defined by a repeating circulation structure that becomes part of the architecture of life itself. A world where the same climate geometry keeps returning, the same habitats keep surviving, and the same weather patterns become part of the biosphere's foundation. And if that kind of climate stability exists, then the next question becomes even more dangerous. Because once the weather stops being the obvious obstacle, you are forced to confront the possibility that one of the most important biological systems on the planet may actually work better than people expect. Can a planet around a redder, dimmer star still run something like photosynthesis? Or does the whole energy chain break before complex life even gets started? This is where a lot of old sci-fi thinking fails. People hear alien stars and they assume plant-like life must be weak, slow, or barely possible. But the science does not really support that simple picture, especially not for a K-dwarf world like Kepler-442b. A 2024 experiment tested this directly. Researchers exposed garden cress and the cyano, Bacterium crucoccidiopsis, to simulated K-dwarf light using conditions meant to represent a habitable zone planet with an Earth-like atmosphere. The result was not that photosynthesis shut down under strange light. It did not collapse into some weak emergency mode. Photosynthesis stayed active, and in some cases it stayed very effective. That matters a lot, because it means light-driven biology under a K-dwarf is not just a theoretical possibility people keep repeating. There is actual experimental support showing that familiar Earth organisms can still function under that kind of illumination. The plant result is especially important because it cuts directly against the lazy version of the story. In that study on day 9, garden cress under solar light showed a photosynthetic efficiency around 0.777, while under simulated K-dwarf light, it showed about 0.781. The difference was not statistically significant. In plain language, the plant was not visibly failing under K-dwarf conditions. That gives you a very strong baseline point. Earth-style oxygenic phototrophy is not automatically crippled just because the star is cooler and redder than the sun. That does not mean garden cress would thrive on Kepler-442b exactly as it does on Earth. It does not mean alien ecosystems would look like farmland, forests, or meadows. What it means is more specific and more useful. The basic machinery of harvesting light to drive oxygen-producing photosynthesis can still work under a K-dwarf spectrum. That is a much more serious statement than maybe something plant-like could exist. It means one of the most important energy pathways in Earth's biosphere still makes scientific sense under this kind of star. Then the cyanobacteria result makes things even more interesting. In the same study, Crucidiopsis did not just survive the K-dwarf lighting conditions. In some measurements, it actually responded significantly better to the K-dwarf radiation than it did to solar radiation. That is not proof that Kepler-442b has oceans full of oxygen-producing microbes. But it is exactly the kind of result that prevents astrobiologists from dismissing K-dwarf biospheres as weak by default. If anything, it suggests that some light-harvesting organisms may find that redder environment very workable, maybe even favourable in certain ways. That changes the whole conversation, because now the question stops being, can photosynthesis work at all? And becomes, what kind of photosynthesis becomes dominant? On Earth, one stellar spectrum shaped the long story of biology. On Kepler-442b, the incoming light is shifted. The balance of wavelengths is different. The atmosphere may filter the light differently. The climate may favour water-dominated habitats or cold margins. So the likely result is not Earth vegetation repeated in a new place. The likely result is selection pressure, pushing life toward pigments, structures, and ecological strategies that are tuned to the actual light available there. That could mean microbial mats spreading across shallow marine environments. It could mean compact surface photo troughs built for lower angle or lower intensity light. It could mean organisms that specialise in wavelengths Earth life uses less aggressively. It could also mean that water depth, cloud cover, and atmospheric filtering become even more important than they are on Earth in deciding where the most productive ecosystems form. On this planet, the useful light may still be enough, but the biological winners may be very different. And there is another reason this matters. Photosynthesis is not only about feeding a biosphere, it is also about changing a planet. Once light-harvesting life becomes productive enough, it starts affecting gases, chemical cycles, nutrient pathways, and potentially even long-term climate. That is where the Kepler-442b story becomes more dangerous in a good way. If phototrophy or phototrophy is plausible there, then you are no longer talking about isolated microbes barely surviving in a few niches. You are talking about the possibility of a biosphere that can actually do work on a planetary scale. Then the atmosphere enters the story again, but this time from the biosignature side. Work by Arnie on K-dwarf biosignatures showed that in oxygenated atmospheres, a planet around a K6 Phi star can support roughly an order of magnitude more methane than an equivalent planet around a Sun-like G2V star. The planet-star contrast can also be better. In simple terms, the same kind of star that changes the light environment may also make certain living atmospheres easier to detect in principle. That is a huge point, because it means the K-dwarf setting may not just allow life to function. It may also make some atmospheric signs of life more visible if the chemistry lines up the right way. That does not make Kepler-442b easy. It does not guarantee a detectable biosphere. It does not guarantee oxygen or methane will build up to useful levels. But it does change the logic again. The redder star is not only a challenge for biology, it may also be an advantage for the legibility of biology, at least under some atmospheric conditions. So the same system features that first looked alien and difficult can turn out to be exactly the features that keep the life question alive. This is why photosynthesis is one of the smartest bets you can make if life exists there. Not giant trees, not earth-coloured forests, not big cinematic jungles. Those are the wrong level of confidence, but some form of light-harvesting biosphere, that is absolutely defensible. Microbial phototrophs in shallow water, photosynthetic mats along stable wet surfaces, low-light specialists in protected zones, maybe even more complex plant analogues, if the atmosphere, hydrology, power and surface conditions cooperate over long timescales. That is not fantasy. That is where the evidence points if you stay disciplined. And that has a big consequence for how you think about the whole world. Kepler-442b is not automatically too dim for productive biology. It is not automatically too red for oxygenic phototrophy-like systems. It is not automatically limited to a weak, marginal biosphere. The stronger scientific position is that if the climate and atmosphere are workable, then some kind of substantial light-driven ecology could be one of the most likely outcomes. The question is not whether life gets enough light to do anything meaningful. The question is what form that meaning takes once the star, gravity, weather, and surface layout all stop being Earth-like. That is what makes this section so important. It removes one of the easiest ways to dismiss the planet. You can still argue about atmosphere, rotation, oceans, surface pressure, or long-term climate. Those are real problems. But the simple claim that a K-dwarf planet must be too dim or too red for serious photosynthesis is much harder to defend now. Actual experiments have made that lazy version of the story weaker. So if life exists on Kepler-442b, phototrophy is not some fringe possibility. It is one of the leading possibilities. A light-using biosphere may be one of the most realistic outcomes the planet can produce. And once that becomes plausible, the next question gets even more dangerous. Because a living atmosphere is not just something a planet has. It is something we might try to detect. And that is where the whole problem becomes both more tempting and more deceptive. What if one day we detect something that looks like life on Kepler-442 and it still does not settle anything? That is the next problem. Biosignatures sound simple in headlines, but they are not simple in real science. On a planet like this, the atmosphere could become both more tempting and more dangerous to interpret at the same time. Start with the most common mistake. Oxygen alone is not a mic drop. It is not the kind of signal where you see it once and declare the case closed. Modern biosignature research is very clear about that. Oxygen and ozone can be produced in non-biological ways under the wrong conditions. They can also build up through atmospheric processes that have nothing to do with a living world that looks anything like Earth. So even if a future telescope somehow saw oxygen around Kepler-442b, that would not be the end of the story. It would be the beginning of a serious argument. That argument would need context, and a lot of it. You would need to know whether there is water. You would need to know the amount of carbon dioxide. You would want methane measurements. You would need to understand the star's ultraviolet environment, because that changes atmospheric chemistry in major ways. You would need some handle on the temperature structure and the broader atmospheric setup. In other words, oxygen by itself is not enough. On Kepler-442, any serious claim about life would have to be built from a combination of signals, not one dramatic line in a spectrum. That sounds like bad news, but then the K-dwarf part of the story helps again. Work by Arnie showed that K-dwarfs may give oxygen plus methane biosignatures a real advantage compared with sun-like stars. Methane can survive longer photochemically around a K-dwarf than it does around a G-dwarf, like the Sun. At the same time, the contrast between the planet and the star can be more favourable. That means if a living atmosphere is actually there, the combination of gases that matters most may be easier to pick out than it would be around a star more like our own. That does not mean a K-dwarf turns biosignatures into easy mode. It just gives you leverage. If a planet around a K-dwarf has an oxygen-rich atmosphere, and also maintains methane at meaningful levels, that combination becomes more interesting because methane is harder to keep around in an oxygenated atmosphere without a strong source. On Earth, life helps maintain that imbalance. So when people talk about biosignatures, they are often really talking about atmospheric combinations that should not last long together unless something keeps renewing them. K-dwarfs can make that kind of imbalance more detectable in principle. But then the catch comes back immediately. The star's history can still create confusion. High-energy radiation changes photochemistry. It affects atmospheric escape. It can alter how oxygen and ozone build up or get destroyed. Under the wrong conditions, a lifeless planet can end up looking more biologically suggestive than it really is. The newer work on K-star ultraviolet and X-ray environments made this point harder to ignore. Yes, K-dwarfs may be friendlier than many M-dwarfs in some ways. Yes, they may preserve certain biosignature advantages, but the advantage is not clean enough to remove ambiguity. Kepler-442b would not just need life to exist. It would need the right atmospheric history for that life to become legible instead of misleading. That is a very uncomfortable idea, because it means even a genuinely promising world might still be hard to read honestly. A living atmosphere is not just a product of biology. It is a product of biology plus the star, plus the planet's chemistry, plus its escape history, plus its climate, plus the way the atmosphere processes radiation over time. If any of those pieces go the wrong way, the signal becomes muddy. So even a correct detection could still be wrapped in uncertainty. And then there is the opposite problem, which may be even worse. The biosphere could be real and still remain almost invisible to us. A planet dominated by oceans, microbes, or low oxygen metabolisms might be biologically rich without producing a loud atmospheric signature over interstellar distance. Life does not automatically advertise itself. A world can be active, productive, and full of living chemistry while still failing to generate the kind of atmospheric imbalance that distant observers can detect easily. Earth itself did not become obviously oxygen-rich for most of its history. That should be a warning. So, habitability and detectability are not the same problem. This is one of the hardest lessons in astrobiology, and Kepler-442b may be a perfect example of it. A planet can be genuinely habitable, maybe even inhabited, and still remain frustratingly quiet in the data. If life there is mostly microbial, mostly marine, mostly hidden below the surface, or mostly running on metabolisms that do not flood the atmosphere with dramatic signals, then the planet could stay biologically important while still looking ambiguous from far away. That is the real scientific sting in this world. Kepler-442b might be one of those planets where the conditions for life are better than the conditions for detecting life. It might be a place where the climate works, phototrophy works, the atmosphere persists, and ecosystems do real planetary work. But the biosignature still comes through weakly, or not at all. In that case, the planet would be promising in the habitability sense and maddening in the observational sense at the same time. So now the problem cuts in both directions. The atmosphere could lie because lifeless chemistry can imitate pieces of a biosignature under the wrong circumstances. Or life could whisper too softly, because a real biosphere does not always generate a clean signal that stands out from space. That is why Kepler-442b is such a strong test case for serious thinking. It forces you to accept that the greatest evidence of life might still be ambiguous, and the greatest ambiguity might still come from a lifeless atmosphere. That is not a failure of science. It is the real shape of the problem. Science is not about finding one magic gas and declaring victory. It is about building context, testing competing explanations, and learning how planets can fool you. Kepler-442b matters because it sits right inside that difficulty. It is close enough to the right conditions to make the search meaningful, but far enough from certainty that every possible clue would have to be handled carefully. And that changes the emotional logic of the whole planet. It is not just a distant, maybe habitable world anymore. It becomes a reminder that living planets do not have to be obvious, and lifeless planets do not have to be honest. The same atmosphere that might carry the best signs of life could also carry the best false alarm. The same world that seems ideal for biosignature searches in theory could still refuse to give a clean answer in practice. So if we ever do look at Kepler-442b closely enough to search for life, the first meaningful signal would not end the debate, it would sharpen it. And that sets up the next question, because once you realize the evidence may stay ambiguous, you are forced to ask a more grounded thing. If life is really there, what is the most likely version of it? What is the most realistic kind of life on a planet like Kepler-442b? If life is really there, probably not anything cinematic, probably not giant animals, not intelligent observers, not surface ecosystems that look familiar from Earth. The most likely version is something much tougher, much simpler in structure, and much harder to notice from a distance. If life exists there, the smart default is not spectacle. It is persistence. The system may be old enough for biology to have had time to matter. Archive solutions put the star's age broadly around 3 billion years, although the uncertainty is still large. That is important because it means the system is not obviously too young. There has likely been enough time for life to begin, adapt, spread, and start affecting the planet's chemistry, if the environment stayed stable enough for long enough. So time by itself is probably not the main obstacle here. The bigger obstacle is continuity. Did the atmosphere last? Did the climate stay usable? Did the surface or ocean environments remain stable enough for life to keep going instead of restarting, retreating, or collapsing? That is why microbes are the smartest default. Not because imagination is being limited, but because microbes are what biology does best when conditions are uncertain. They can survive in a wider range of temperatures, chemistries, and energy environments. They can exploit weaker gradients. They can live in water, under ice, in sediments, in rock pores, near hydrothermal activity, and in many settings where more complex life would struggle or never appear at all. So given what we do not know about Kepler-442b, the atmosphere, the oxygen level, the geology, the surface layout, the weather system, the most defensible prediction is not a planet covered in obvious complex organisms. It is a microbial world, or at least a microbial-dominated one. That is not a weak answer. On Earth, microbial life ran the planet for most of its history. Microbes reshaped the atmosphere. They transformed ocean chemistry. They drove redox cycles, nutrient cycles, and long-term biological change on a planetary scale. So when you say microbial biosphere, you're not talking about a failed planet. You're talking about a planet where life may be doing enormous amounts of work without producing anything that looks impressive to a human observer standing on the surface. Then the next point sharpens the argument. Complex life demands a long list of victories, not just one. You need climate stability over long time scales. You need persistent access to useful energy. You need nutrient cycling that does not collapse. You need an atmosphere that remains supportive. In many cases, you also need a route toward oxygen-rich or otherwise high-energy metabolisms that can support more demanding organisms. A K-dwarf planet can plausibly offer very long timescales, and that helps. But long time alone does not guarantee the rest. Kepler-442b might have the clock needed for complex evolution, while still lacking one or two other conditions that keep life from ever becoming anything remotely animal-like. That is the key escalation here. A planet does not need to fail completely in order to remain simple. Kepler-442b might host real life and still never produce anything human scale, or anything Earth-like above the microbial level. It might remain a world of mats, films, plankton-like organisms, shallow water phototrophs, buried chemotrophs, or low-complexity multicellular life if conditions permit it. The line between inhabited and full of familiar complexity is much larger than people usually admit, but the long lifetime of the star is still a huge advantage. And that is why K-dwarf planets remain so attractive. K-dwarfs can live far longer than sun-like stars. That means if a biosphere manages to survive the difficult early phases and the planetary environment stabilizes, it can get an enormous evolutionary runway. Not millions of years only, but potentially much longer periods in which biology can experiment, adapt, spread, and reshape the world. K-dwarf worlds may not always be easier to start, but they can be easier to sustain over deep time once the system settles down. That is one of the strongest reasons Kepler-442b stays scientifically compelling. If life got established there, and the atmosphere remained supportive, then the planet may have had immense stretches of time to let that life become chemically significant. Even if it never became complex in a way humans would recognize, it could still have spent huge spans of time altering oceans, sediments, gases, and surface chemistry. A long-lived microbial biosphere is not a small result. It is one of the most powerful kinds of biosphere a planet can have, because it can keep working for ages. So if life exists there, it may be ancient, subtle, and planet-shaping without being obvious. It may not be loud, it may not be intelligent, it may not build giant organisms or colourful land ecosystems, it may never become easy to detect. But it could still have changed the chemistry of the air, the water, the seafloor, and the surface over immense timescales. It could have altered redox cycles, nutrient pathways, methane production, carbon storage, and mineral interactions in ways that matter enormously, even if no human-style observer would ever look at the surface and call it spectacular. That is probably the most realistic way to think about Kepler-442b, not as a second Earth waiting to surprise us with obvious alien landscapes, but as a world where life, if it exists, is more likely to be durable than dramatic, more likely to be chemically powerful than visually impressive, more likely to spend millions of years changing the planet quietly than to produce anything that fits our favourite science fiction images. And that should change the emotional expectation too. The most realistic alien world is often not the flashy one. It is the one that has been biologically busy for an incredibly long time without ever needing to resemble Earth's favourite forms. A world where life survives because it is efficient, adaptable, and hard to erase. A world where being alive is not about looking extraordinary, it is about lasting. So if Kepler-442b is inhabited, the most probable version is not cinematic. It is stubborn. It is a biosphere that keeps going, keeps adapting, and keeps changing the planet without promising anything familiar in return. And that leads straight into the next tension, because even if microbes are the smart default and deep time is on the planet's side, none of that guarantees safety. The star can still help the planet and hurt it at the same time, and that balance may decide whether life stays on the surface, retreats below it, or never gets a stable hold at all. Can the same star that gives lifetime also slowly damage the planet the whole time? That is the next hard part of Kepler-442b. By now the system may sound promising, compared with many red dwarf planets, and in some ways it is. But better than the worst case is not the same thing as safe. The host star still matters, and it matters all the way down to whether the atmosphere survives, whether the surface stays protected, and whether biology can keep working in exposed environments over long spans of time. This is one of the most important corrections in the whole story. Stellar activity is not some side detail you mention once and move on from. Studies of habitable zone Kepler planets treated things like X-ray flux, magnetic pressure, stellar mass loss, and general activity as central parts of the habitability problem. Not background noise. Central parts. Because the star does not just shine on the planet, it pushes on the atmosphere, affects escape, alters radiation at the surface, and changes the long-term odds that a planet can hold on to the conditions life needs. And Kepler-442 is not in the worst category. That matters. In the relevant comparisons, it did not look as catastrophic as the harshest flare stars in those samples. So this is not one of those obvious nightmare cases where the star makes the planet look nearly hopeless from the start. But the paper still treated the stellar environment as a major factor, because even a less violent star can still shape atmospheric survival in ways that matter over billions of years. On a world like Kepler-442b, the star does not have to be extreme to still be consequential. Then the next question becomes more specific. Could the planet protect itself magnetically, at least to some degree? There is at least some room for that. In the same study, under Earth-like magnetic assumptions, planets in the sample could, in principle, sustain magnetospheres large enough to offer meaningful shielding, and for Kepler-442b, the model gave an example magnetosphere standoff, distance of around 12 planetary radii. That is not a direct detection of the planet's magnetic field. No one has measured a real magnetosphere there, but it is still an important clue. It says a magnetically protected version of the planet is not absurd. That matters because a magnetic field can help buffer the atmosphere from some of the star's influence. It does not solve everything, and it does not make a planet invulnerable, but it can reduce direct stripping effects and change how charged particles interact with the upper atmosphere. So if Kepler-442b has an active interior and a magnetic dynamo strong enough to matter, that could be one more factor helping the atmosphere persist. Again, the pattern repeats. The planet does not become easy, but another route to long-term stability stays open. But then the caution returns. The old idea that K-dwarf planets might be super habitable, by default, has been weakened over time. Not destroyed, but weakened. Later hazmat work showed that K-star ultraviolet output can stay elevated longer than some earlier optimistic pictures suggested. That does not mean Kepler-442 is as punishing as a bad M-dwarf. It does mean you cannot casually assume the star's history was gentle. The UV environment may have stayed significant for a long time, and that matters because ultraviolet radiation feeds directly into atmospheric chemistry and surface exposure. So Kepler-442b ends up in a much more interesting middle space. Maybe better than many M-dwarf planets, yes, but not effortlessly safe, not automatically calm, not Earth, but under a nicer long-lived star. That middle space is exactly where the serious science sits. The planet may have enough advantages to stay in play, while still carrying enough stellar risk that habitability has to be earned, not assumed. And this is where one of the biggest Earth biases has to be dropped. Even if the surface is rough at times, that does not kill the life question. It may just move life somewhere else. On Earth, life is not only a surface phenomenon. It lives in oceans, in sediments, in rock pores, in ice below the ground, around hydrothermal systems, and in many environments that are naturally shielded from radiation and climate extremes. So even if Kepler-442b had periods of elevated surface stress from stellar activity, that would not end the possibility of a biosphere. It would only change where the safest and most persistent habitats are. That is a major point, because people often picture habitability in a very surface-centered way. They imagine that if the open surface is difficult, the world is mostly done. But for microbes especially, that is not true. Oceans can absorb and buffer a lot. Sea ice can protect what sits below it. Sediments can shelter chemistry and life for huge spans of time. Caves and subsurface aquifers can become long-term refugees. So a planet does not need a permanently gentle surface everywhere to remain biologically important. It just needs stable niches that life can reach and keep using. That makes the system harder to dismiss and harder to simplify at the same time, because now Kepler-442b does not need to be a comfortable open-air paradise to stay interesting. It could be a harder planet, one where the surface is only intermittently favourable in some places, while the real long-term biological engine runs in the ocean, under the ice, or underground. In that case, the star may still be shaping life strongly, but not by preventing it, by selecting where it can safely persist. And that leads to the real planetary tension. Kepler-442 is a persistent star, but an imperfect one, not a dead, quiet star, not a killer star, a star that gives the planet time, gives it redder light, may spare it some of the worst X-ray punishment seen around harsher red dwarfs, but still carries enough UV complexity and activity history to keep the environment from ever being trivial. That is the kind of host star that makes a planet scientifically dangerous, because it opens the door without removing the test. That is why Kepler-442b may be habitable, precisely because it is difficult, not because it is comfortable. A world can become biologically important not by avoiding every challenge, but by surviving a narrow balance of them. Enough air retention to stay in the game, enough shielding to avoid collapse, enough environmental stability to let life adapt instead of reset, enough time for chemistry to become ecology, and ecology to become a biosphere. That is a harder route than the easy fantasy version, but it is also a much more realistic one. And that realism raises the stakes, because it means Kepler-442b is not just a yes or no habitability case. It is a planet where difficulty itself may be part of the reason the answer remains open. The star may have challenged the atmosphere without destroying it. The surface may have been stressed without being sterilized. Life, if it exists, may have survived not because conditions were perfect, but because they were good enough for long enough in the right places. That is exactly the kind of world astrobiology has to take seriously. Not a paradise planet, not a dead world. A planet under pressure, with enough support to keep the life question alive, and enough risk to stop anyone from getting comfortable. A world where the star helps and hurts at the same time, and where the outcome depends on how the planet responds over deep time. And now the story hits one more frustrating turn, because even if Kepler-442b really is one of the better long-range candidates, that does not mean we can read it properly anytime soon. In fact, one of the worst things about this planet may be that it is good enough to matter, but too hard to study well. Why can one of the most interesting planets still remain one of the hardest to understand? Because Kepler-442b has the kind of numbers that make scientists care, and the kind of observing conditions that make scientists suffer. This may be one of the better long-range habitability candidates we know about, but it is attached to exactly the kind of system that current tools struggle to read properly. The problem starts with the star. Kepler-442 is faint, around magnitude 15.3 in visible light. It is also far away, about 366 parsecs, roughly 1,190 light-years from Earth. And the transit signal from the planet is small, only about 0.05 to 0.06%. Put those facts together, and you get the core observational problem immediately. This is a scientifically valuable planet around a relatively dim and distant target, with only a shallow transit to work from. That is not the kind of setup that makes atmospheric follow-up easy. And that matters because atmospheric characterization is where the whole argument would really start moving. If you want to know whether Kepler-442b has a thick atmosphere, a thin atmosphere, water vapor, carbon dioxide, clouds, methane, oxygen, or anything else that would help settle the habitability question, you need a target that telescopes can actually read with enough precision. Bright stars help, nearby systems help, deep signals help. Kepler-442b does not offer much of that. The planet is compelling in theory, but difficult in practice. That is exactly why other worlds are getting more telescope time. The exoplanet community has been forced to prioritize systems that are closer, brighter, and easier to study with current instruments. If you only have so much observing power, you point it where the odds of getting a usable atmospheric signal are highest. That usually means planets around nearby small stars with stronger observational leverage. So even though Kepler-442b remains important, it is often treated less like an easy, near-term laboratory target and more like a benchmark in the larger population of potentially habitable rocky candidates. That distinction matters. Kepler-442b is not fading from the conversation because it stopped being interesting. It is staying in the conversation because it is scientifically important, even while being observationally inconvenient. It helps define the theoretical landscape. It gives researchers a case study for how to think about habitability on a temperate super-Earth around a K-dwarf. It keeps pressure on models of climate, atmosphere, rocky composition, volatile retention, biosignatures, and long-term evolution. But it does all of that without offering the kind of clean near-term observational path people would want. And the frustrating part is that the star type itself is not the problem. K-dwarfs are still excellent stellar targets in principle. Work like Arnie's makes that clear. K-dwarfs can be attractive for biosignature studies because they offer useful planet-star contrast and favourable methane-oxygen chemistry compared with Sun-like stars. So the tragedy of Kepler-442b is not that it orbits the wrong kind of star. In many ways, it orbits one of the more interesting kinds of stars you could ask for. The tragedy is that this specific system is too faint and too far away to exploit easily with the tools we have right now. That makes the whole case more painful because the architecture is attractive. A potentially rocky planet around a K-dwarf with a promising orbit under a star class that people genuinely care about for astrobiology should be exactly the kind of system you would want to study deeply. But distance is cruel. Brightness is unforgiving. And with current methods, those limits matter. So Kepler-442b stays just close enough to the right physics to remain valuable, and just far enough from observational accessibility to remain frustrating. But that does not make it less important. In some ways, it makes it more important. Planets like this anchor the theory space. They force scientists to test how habitability metrics are being used. They challenge assumptions about where the rocky to volatile boundary really sits. They pressure climate models to handle redder stars, stronger gravity, shorter years, and uncertain atmospheres without collapsing into Earth-only thinking. They keep the whole field honest by asking a simple but difficult question. What exactly do we mean by Earth-like, when almost every major boundary condition is different? That is why Kepler-442b has power even without a decisive spectrum. It is not only a target, it is a stress test for the framework itself. If a planet can be close to habitable while orbiting a cooler star, living under stronger gravity, receiving a different spectrum, and possibly running on very different climate logic, then the old categories start looking too narrow. Earth-like no longer means looks like Earth in all the obvious ways. It starts meaning something more flexible, more physically grounded, or often much less human-centered. And that is the deeper reason this planet matters. It is not just a candidate for life, it is a candidate for breaking the categories people got comfortable with early in the exoplanet era. If Kepler-442b, or a world very much like it, can sustain a real biosphere, then the universe may contain many habitable planets that would have been filtered out by simpler expectations. Planets that are a little heavier, a little dimmer, a little redder, a little stranger in timing, a little less obviously Earth-like, and still fully alive. That possibility changes the whole search. It means the challenge is not only finding Earth copies, it is learning how broad the living world category really is. Kepler-442b sits right in that argument. Not fully readable, not fully dismissible, not settled, not irrelevant. A planet that may remain hard to study for a long time, and still forces the field to ask better questions right now. So the most frustrating part is also the most valuable part. Kepler-442b may be one of the best candidates we still cannot read properly, and because of that it keeps exposing the gap between detection and understanding. We know enough to take it seriously. We do not know enough to close the case, and that gap is exactly where modern astrobiology lives. Which brings the whole story to its final tension. After all the uncertainties, after the gravity, the light, the climate, the atmosphere, the weather, the biosignatures, and the observational limits, the real question is no longer what would life look like. The real question is which version of life actually survives the logic of this planet. So after all of that, what is the real answer on Kepler-442b? Not what would life look like. The better question is much tougher. Which version of life actually survives the rules of this planet? Start with the optimistic version, because it is still scientifically possible. In that version, Kepler-442b really is a rocky super-Earth. The gravity is around 1.3 g, strong enough to change biology, but not so strong that the surface becomes unworkable. The atmosphere is thick enough to hold heat, move moisture, and keep oceans liquid, but not so thick that the planet turns into a deep volatile world with no familiar surface conditions. The magnetic shielding is good enough to help protect the air over long time scales. The K-dwarf light environment turns out to be stable and usable enough for photosynthesis like life to work. In that case, life could begin in the ocean, stay microbial for a very long time, and then slowly become more complex in forms shaped by heavier gravity, redder light, and a different climate system than Earth ever had. That version is not fantasy, it is not proven, but it is grounded. It uses the best case reading of the actual numbers, the actual climate logic, and the actual biology experiments. In that version, Kepler-442b is not Earth 2.0. It is a genuinely different living world that still solves the same basic problems: keeping water liquid, holding onto an atmosphere, harvesting light, and letting evolution work for long enough to matter. But then there is the pessimistic version, and that one is still alive too, In that version, the planet is not the kind of rocky world people want it to be. Maybe it is too volatile rich. Maybe it is covered by an ocean so deep that the whole Earth-style surface logic breaks down. Maybe the atmosphere is too thin and the surface stays cold and marginal. Maybe the atmosphere is too thick in the wrong way and the planet becomes a heavier, deeper, less accessible world than the habitability headlines suggested. Maybe the star's history was harsh enough to damage long-term surface habitability early on. In that version, the famous Earth-like label turns out to be a mirage built mostly from radius, orbit and hope, and that possibility is not some unfairly negative reading. It is also scientifically real. Kepler-442b became famous because it sits near the right boundaries, not because it has already crossed them in our favour. It is close enough to habitability to deserve serious attention, but not well constrained enough to settle the argument. That is why the optimistic and pessimistic versions both still have room to exist. The most realistic answer is probably between those extremes. If life exists there, the highest probability version is likely not a second Earth, with blue skies, open continents, forests and familiar animals. It is more likely a world where climate, chemistry and light allow durable ecosystems that are microbial, aquatic, mat-forming, low oxygen, or biochemically conservative in ways Earth does not train you to expect. But that does not make the biosphere less real. It would still be fully alive. It could still be global in effect. It could still change the atmosphere, the oceans, the minerals, and the chemistry of the surface over very long periods. That point matters because people often make the same mistake over and over with exoplanets. They treat not Earth-like in appearance as if it means less alive or less important. But on a planet like Kepler-442b, the most realistic biosphere may be one that does enormous planetary work without producing anything visually familiar. It may be shallow water phototroughs. It may be microbial films. It may be ocean-dominated ecosystems. It may be a world where the biologically important chemistry happens in water columns, sediments, ice margins, or subsurface environments instead of across broad green continents. And that is the part that really forces a bigger shift in thinking. Because if Kepler-442b hosts life, then habitability is not a narrow filter that only lets in near copies of Earth. It is a wider possibility space. A planet can have stronger gravity, a shorter year, redder daylight, different snow and ice behaviour, different atmospheric chemistry, different weather logic, and still converge on biology. Not the same biology, not the same landscapes, not the same planetary feel, but biology all the same. That changes the search in a serious way. It means the universe may not be waiting for us to find Earth duplicated over and over. It may be full of worlds that solve the problem differently. Worlds that are colder overall but still biologically active. Worlds with denser air. Worlds with shorter orbital clocks. Worlds where ocean life matters more than land life. Worlds where the dominant photosynthetic systems are tuned to a different spectrum. Worlds where life survives because it is adaptable, not because the planet is comfortable. And Kepler-442b is such a powerful example because it brings all of those pressures together in one case. Stronger gravity, but maybe better atmospheric retention. A dimmer star, but maybe a longer lasting one. Redder light, but still usable for photosynthesis. A potentially good orbit, but an atmosphere we do not know. A planet that may be stable enough for life, but not simple enough for us to read easily. Every part of the system keeps doing the same thing. It complicates the easy story and keeps the serious one alive. So the real answer is not a visual answer. It is not about whether there are trees, animals, oceans, or coastlines in the exact way humans want to picture them. The real answer is about which version of life can survive this planet's logic. Which kind of biosphere can work under a K-dwarf? Which kind of metabolism can persist with this light? Which kind of climate can remain stable under this atmosphere? Which kind of body plan, if complex life ever appears, can handle the gravity, the timing, and the environment? And once you ask it that way, the planet becomes much more important than a simple yes or no life candidate. It becomes a challenge to the whole Earth-centered habitability framework. If life can survive there, then many worlds we used to treat as marginal may not be marginal at all. They may just be different in ways our early categories were too narrow to capture. That is why Kepler-442b matters so much, even now, while the key facts remain unresolved. It may be too far away and too faint for us to settle the question anytime soon, but it is close enough to the right physics to force a bigger view of the universe. It sits close enough to the habitable boundaries, close enough to the right kind of star, close enough to the right size, and close enough to the right biological possibilities that it keeps pushing the field to think harder. And the most honest final answer is also the most interesting one. If life exists on Kepler-442b, it probably did not copy Earth. It probably solved the problem of being alive under a K-dwarf in its own way, under heavier gravity, under redder light, under a shorter year, under a climate system we still cannot fully pin down, under atmospheric rules we still cannot read from here. That is the real closing point. Kepler-442b does not matter because it looks like a second Earth. It matters because it may be a living world that makes the Earth copy idea feel too small. If life is there, then a habitable planet is not one narrow design. It is a much larger category than we were comfortable with. And that means the universe may be filled with living worlds that do not look familiar enough to satisfy our first instincts, but are alive anyway. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video